So number 6 then from the 2009 Advanced Higher Complex Numbers. Change this rational expression involving complex numbers into a single complex number, it says, in this form. And then show that number in an Argand diagram and get the modulus and argument. Well, the first thing is, of course, you won't be showing it exactly in this form. That's just a convention in that when A and B are unknown, they would assume the positions of variables, which is in the second place in a term, where I would just be like its coefficient. Whereas once you know A and B are, it would normally be written this way, with the real numbers first and then the I afterwards. Well, first step would this be, get that top sorted. Square out that bracket. Square the first, square the last, twice the product. So square the first one, square the last would be 4i squared, so it'll be minus 4. Twice the product, doubling the 2 plus 4i over the 7 minus I. So that means you've got negative 3 plus 4i over 7 minus I. Now, make the denominator real by multiplying that complex number by its conjugate. Multiply the top, the numerator, by the same thing, so the fraction stays the same. And of course, by using the conjugate, you form the pattern for the difference of two squares. Except, in terms of complex numbers, you've actually formed the pattern for the factorisation of the sum of two squares, because I squared is negative 1. So actually the pattern would be 7 squared, 49, and then the 1 being the number of I, plus 1. And then for the top, I've got negative 21 for the firsts. I've got minus 4 again, because it's 4i squared minus 4. And then I've got 28, take away 3 is 25i. Tidy that up a bit. It's all very handy because I've got minus 25 plus 25i to match that bottom 50 very nicely. So that's just going to give me halves. So I've got negative a half plus a half I for z. Notice, not quite in that form because I've got the number first and the I second, but that would do. Now for the second part, show this number in an Argand diagram. Well, an Argand diagram is just a graphical representation where you show the real part as the x and the imaginary part as the y coordinate. Now, strictly speaking, this number is just shown as a point, and that's quite easily done, because it would be negative a half for the real part and then a half for the imaginary part, putting the point there. So that would be a half, and that would be at negative a half. However, when it says find the modulus and argument of it, that more refers to the position vector of that, considering it as polar coordinates. So you could draw a line. That line isn't necessarily part of the complex number. That line just indicates the position vector of that complex number. And when it talks about the modulus and the argument, it means the length of that line and the angle that that line makes to the real axis. So the length of that line would be the modulus, and the angle round from the real axis would be the argument of it. Well, that's just the same as in polar coordinates. You'll get the length of that line from the squaring of the two components. So I've got to get the modulus of z, which means the length of its position vector. I would have squaring its components would be a negative a half squared, and for the other component a half squared, not a half I, because it's only the components of it, which is going to give me, well, immediately you know what that's going to be. It's going to be half root 2 because you've got a square. And in a square, the ratio of the sides are 1, 1, root 2. So that happens to be a half, that must be a half root 2. I think I'll just jump straight into that. So z equals a half root 2. Rather than just going through all these fractions and taking up lots of space. Now, the argument takes a little bit of care. To get the argument of z, then of course I'm going to use in trigonometry with this vertical over the horizontal, which is the tangent, and you would normally think, well, for the argument I just write this. It's going to be inverse tan of the two components, and if I'm calling them a and b rather than x and y, it would be b over a. That's the imaginary over the real components. But that's not strictly true, because the range of the inverse tan only goes from pi upon 2 to negative pi upon 2. It's not going to take you all the way around, no matter which numbers you put into this. The answers for inverse tan, I'll just put up here, The range of inverse tan of anything you put into it lies between pi upon 2 and negative pi upon 2. And of course that's no use for the argument, because the argument means the angle from the positive real axis all the way round to wherever it is, going up to pi, and if it happens to be below, then going backwards, in other words finding the shortest way to it, up to negative pi, but not including negative pi. So that doesn't go far enough. No matter what number you put in there, you'll only get an answer which is either in the first quadrant or in the fourth quadrant. You have to realise yourself that you need to go slightly further. To create a proper function for this, I would need a second part that would be along the lines of, the argument is actually this, plus some number of pi, where, I know this seems a bit tedious because you can just do it by inspection by considering the diagram, but I'll just mention it anyway, where, if the points in the first quadrant, all's fine. A's positive, B's positive, inverse tan of the positive gives me an angle between 0 and pi upon 2. If I'm in the fourth quadrant, where A's positive and B's negative, in this fourth quadrant, inverse tan of that negative amount will give me a negative answer, which will be in this quadrant between 0 and negative pi upon 2. So that's fine. But if the point's in the third quadrant, where A is negative and B is positive, that quantity is still negative. Applying the inverse tan to a negative quantity gives you an answer in the fourth quadrant. I don't want the answer in the fourth quadrant. I want the answer in the second quadrant. You would have to add pi onto it to get there. Similarly, if that point was in the fourth quadrant, where they're both negative, that would give a positive amount. Inverse tan of a positive amount gives a result in the first quadrant. So if the point was down here, it would give the answer here. So I'd have to come back through pi. So when I say n pi, that n could be 0 or plus or minus 1 as appropriate. But rather than create a little formula for this, I'll just do it by inspection, realising that this will only give me part of the answer, and then I'll have to correct it. So in this case, if I do inverse tan of, and just use it strictly as that, of b over a, it would take me, this point here, would take me into the fourth quadrant, so I'd have to add pi onto it. So when I write this formula down, maybe I should just put that first of all, plus n pi. So the argument of z is going to be inverse tan of, now I know what the answer is anyway, because that's half of a square, it's 45 degrees, it's 135, it's 3 pi upon 4. I know the answer to that, but strictly speaking, working it out as it said, because it said evaluate, I would have to do this. Well, what are the numbers? I've got a half over negative a half. So I'll be working out inverse tan of negative 1. Now, inverse tan of negative 1 would give you negative 45 or negative pi upon 4. I would have to add pi onto that, or add 180 onto it, to get the actual argument, which equals negative pi upon 4 plus pi, which equals 3 pi upon 4. Or 135 degrees if you like.